Transparent Physics proudly presents our next lesson in our Noobster class on adding two-dimensional vectors. Lesson 4, Fall of the Resultant. So hopefully you remember from lesson 3, we talked about how to take two perpendicular components pointing in the x and y direction and build a resultant from them. Well, this time we're going to do the opposite. We're going to take a resultant and rip it apart into its x and y components, still using SOHCAHTOA, but different components of it this time. And in addition, we're going to show how using the standard angle, an angle with respect to the positive x-axis, unlocks the right component every time. It's pretty cool the way it works out, and I look forward to showing it to you. So what do I mean by x and y components? So those are sort of the stars of this particular lesson. Components, a little history lesson back in the day, when we had our stereo systems, they were component stereo systems. Now, realistically speaking, it was my dad's stereo system. We weren't allowed to touch the dials. But he had a stereo system set up where there was an 8-track and like a turntable and an AM/FM receiver, and each of these individual things were purchased separately, and they were assembled together to make a stereo. So you could get sort of a customized stereo based on how much money you wanted to spend and what you wanted it to do and stuff like that. So in that same genre, components in a vector context are the vectors that add together to give you the resultant. They're the pieces that come together to make the whole stereo, if you will. And you can get any number of vectors to add together to give you any sort of value you want to. Really, sort of the metaphor goes, imagine that I have a displacement vector that puts me 13 kilometers to the northeast. There are an infinite number of combinations of paths that I could take that would end up delivering me to 13 kilometers northeast. Any number of routes could get me there. You know, imagine that you're flying with a jetpack and you can just travel straight and turn and travel straight and turn, etc. And again, unlimited numbers of ways that you could end up at that final point. But what's interesting is that there is always a set of paths that consist of only two vectors, and we can go horizontally a certain distance and then vertically a certain distance, and we can create any vector we want to. So, you know, for example, for the 13 kilometers northeast, I could travel a certain number of kilometers to the east. I could travel a certain number of kilometers north, and I end up where I need to be. That works every time. Another way of thinking about it is sort of like the claw game. With the claw game where you go for the prizes, you know, you have two controllers. One only moves left or right. One only moves up or down. But between those two controllers, you can end up anywhere you want to in the playing field. All right, let's talk about first the x component. When I set this up, I usually talk about the horizontal component first. So if we want to go back to the metaphor from the previous slide, when we have a combination of east-west and north-south vectors to create a total displacement, I always drive east or west first. And when we set this up in the picture, that's the adjacent side. If we think about the angle, the interior lower angle there as being the reference angle, the adjacent side is the one that's next to it that's not the hypotenuse. And it represents how far east or west you need to drive, if it's a displacement vector, but it can mean any sort of vector quantity, before you would then need to turn north or south to complete your route. And a metaphor for it maybe is if there is a light shining down from above on the, if there's a light shining down from the top, then the Rx quantity is sort of the shadow that this arrow would make when light shining straight down over it. It's a way that you can think about it. And we can use our SOHCAHTOA quantities to figure out what that would be. Knowing the hypotenuse and knowing the angle, that sets us up as wanting to use the trigonometric identity cosine theta is equal to the adjacent over the hypotenuse, because we know the angle we're starting with the resultant vector, so we know the angle and we know the length of the resultant vector. So we know the r value and we know theta. So all we need to do is solve for the adjacent side, which we've already defined as rx. So if I take the equation cosine theta equals rx over r, and I solve it for rx, we have our x component equation. The x component of your vector is equal to the magnitude of the vector times the cosine of the angle that the vector makes with respect to the positive x-axis. It's that standard angle that we've been referring to over these past couple lessons. So in solving for the y component, we're going to be looking at the next leg in our right triangle, the vertical leg, if you will. Using the displacement metaphor, now that we've driven east or west, we need to travel north or south to get to our final destination. We're always going to draw the y component second. It lines up nicely as the opposite side then. And at this point, we don't need to worry about the rx value anymore. We'll just focus on ry. Again, using the metaphor, if we imagine that we have a light shining from, say, in this case, the left, as the light shines over and hits the resultant vector, ry is the shadow that it, say, would make against the wall. Just another way to think about it. And as before, we have the angle of the hypotenuse, the resultant. We have the length of the resultant. We're going to ignore the fact that we could technically know our x at this point. We're just going to go back to the initial information, the length and orientation of the resultant vector. And in this case, we are going to use the sign. We have the opposite side that we're interested in. We know the angle of the hypotenuse. We know the length of the hypotenuse, which is our resultant vector. So sine of theta is equal to opposite over hypotenuse, which is equal to ry over r. We can manipulate that to solve for ry, and now we have our vertical component, the y component equation. ry equals r times sine theta. That's the length of your resultant vector times the sine of the angle of the resultant vector. And again, that angle is taken as a standard angle with respect to the positive x-axis. And as I pointed out a couple times, standard angles are super important for this step in our lesson. They're going to unlock the proper orientation of the x and y components when we combine standard angles with the trigonometric formulas of sine and cosine. So it's really cool how it does some of the work for us. When we set things up correctly, if the x component ends up being negative, that means that it's pointing to the left. If the y component ends up being negative, that means it's pointing down. And again, we'll show you some examples coming up right now. All right, then, as we're about to dive into the math, a good time to stop and take a sip of tea. If you don't have a cup of tea handy, pause the video, brew yourself one, and come back. Trust me, everything's better with a freshly brewed cup of tea. Okay, so let's take a look at just a real basic one to start. We'll start with vector A, and we'll say that vector A has a magnitude of 42 meters, and it's pointing at 35 degrees. So I always like to start with a sketch just to give a rough idea of what we're looking at here. So vector that's like this. We have a 35-degree angle, and then what we are going to be solving for is we're going to be solving for the x and the y components. So ax is going to be this guy right here. And ay is going to be this guy right here. So we'll solve for each of those individually using the equations that we've talked about. The x component equations are always going to be the same template. Now again, the letter a might change depending on the vector, but the equation is just ax equals a times the cosine
of theta, where A is the magnitude and theta is the angle. So we just literally plug the values in. That's all it comes down to. So let's keep the units so we know what we're getting. 42 meters times the cosine of 35 degrees. Again, make sure your calculator is in degrees, not radians. So I can just type it in literally. Say 42 times cosine, parenthesis opens up for me automatically, quantity 35. So we get a value of 34.4 meters, and that's the AX component. The AY component is equal to the quantity A times sine of theta. So you can see the numbers or the measurements are all the same. 42 meters is the same. 35 degrees is still the same. The only difference is we switch from cosine to sine, that's all. So 42 times the sine of 35 gets us 24.1. So what we just solved for is the idea that the length is 34.4 meters in the horizontal direction, and then it is 24.1 meters in the y direction. So if you were to travel 34.4 meters east and then 24.1 meters north, you would end up 42 meters from where you started at an orientation of 35 degrees with respect to the positive x-axis. Okay, let's take a look at another slightly more complicated resultant breakdown. So we'll call this vector B, and we'll say vector B is 100 kilometers long, and it's oriented at 115 degrees. So if we were to sketch that out, again, we have sort of our x and y axis here. 115 degrees, 90 degrees is straight up. So 115 degrees is 25 degrees past that, so I don't know, around here-ish. So that's vector B, oriented at 115 degrees. So if I draw my x and y components, we're going to see BX starts at the origin and goes over. And then BY starts where BX ends and goes straight up. So based on that picture, I'm going to assume that BX is going to be a negative value and BY should end up being a positive value. So let's see if those numbers work out that way when we solve it out. Again, the equations don't change aside from just the nomenclature indicating what vector we're looking at. So we can solve for BX. BX equals B times the cosine of theta. Now the theta is, again, with respect to the positive x-axis. I'll color code it to match there. So we have 100 kilometers times the cosine of 115 degrees. And when I plug it in, making sure that I'm in degrees, 100 times the cosine of 115. My prediction is the value is going to be a negative, and it is. So the calculator tells us that the BX component is negative 42.3 kilometers. Solving for BY, so I managed to mangle my B, there it is. So BY is going to equal B times sine of theta. Again, B is the magnitude, so that's 100 kilometers. And then we just have the sine of 115 instead. Based on the way my drawing works out, I'm going to assume that BY is going to end up having a larger magnitude and positive. It looks like it's going higher than it is going over. So 100 times the sine of 115. get 90.6 positive. 90.6 kilometers. And that's really all there is to it. We'll go one more just to make sure you got the hang of it. But that's about as complicated as this gets. Okay, third time's the charm. Let's get one more example in here, and just to mix it up a little bit, let's say that we have vector C, and vector C is 16. And again, it doesn't matter. I mean, I could choose any vector quantity, meters per second. 16 meters per second, so we'll get a velocity, and let's say it's going at negative 145 degrees. So again, as long as it's a standard angle, doesn't matter what initial value I give. Just make sure it's with respect to the positive x-axis. So when I take a look to see what vector C is, negative 145, we're going to take 180 as our reference point. And when we compare it to 145, we're going to see that C is about 35 degrees. It's going to start at the x-axis and swing around this way. And it's going to end up about 35 degrees shy of the negative x-axis. So this value here is negative 145 degrees. And it's a velocity vector, 16 meters per second. So I go horizontal first. So again, we are going to have a negative cx value. And when we take a look at the y value, it's going to drop down in this case. So we're going to have a negative cy value as well. So we should expect the equation to give us a negative for both cx and cy. But there's only one way to find out for sure. Let's take a look. So cx is going to equal c times the cosine of theta. Notice again, when we're talking about c, the magnitude is only going to be, again, the size of that vector. There should never be a negative sign associated with c. A negative sign would indicate direction, and that should be accounted for by the angle, not by the magnitude. So watch out, make sure you never put a negative sign in this part of the equation. It only comes through via the angle. And again, the angle can be positive or negative, we don't care about that, as long as it's a standard angle. 16 meters per second times the cosine of 145. 16 times cosine of negative 145. And as suspected, it gives us a negative cx. And that is negative 13.1 meters per second. How about for cy? Again, same equation, c sine theta though, as opposed to c cosine theta. So I guess technically not the same equation. A similar equation, not the same equation. 16 meters per second times the sine of negative 145. Again, my instincts, my physics instincts are telling me that this is going to be a negative value as well based on our drawing. Let's take a look to see if that is true. 16 times the sine of negative 145, and it does end up being. So we've got a value of negative 9.2 meters per second. So there we go, another example. Realistically speaking, not that hard to do. You have to know what your magnitude is, you have to know what your angle is, you have to make sure the angle is with respect to the positive x-axis. But once you have that administrative work set up, the equations work out the same every time, and we're going to see why that's a big advantage when we put all this together in the next lesson.
Okay, so let's wrap up. If we know the magnitude and angle of any vector, we can solve for its x and its y components. Why is that important? Well, knowing how to solve for our vectors x and y components is the final ingredient we need in our recipe for unlocking unlimited vector addition. So everything's there now. We have all the pieces. We're ready to do this. Make sure you tune in for the next lesson. You're going to be amazed at how much you've learned. If you found the content of this lesson useful, feel free to leave a like. If you have any questions about what I talked about, leave a comment. And to be informed of what is the newest release from Transparent Physics, be sure to click subscribe. And thank you for joining us in this lesson where we sort of restore cosmic balance. If lesson 3 taught you how to build vectors together, lesson 4 shows you how to rip them apart. And I hope I've made the process a little clearer for you on this lesson of Transparent Physics.